So, what exactly is the lambda calculus? Well, the lambda calculus is a formal system for expressing computation developed by Alonzo Church. You can see a picture of Church on the right. He was born in 1903 and died in 1995 in the United States. It's called the lambda calculus because, as you will see later, the Greek letter lambda is used to define expressions and terms within the system. There are many variants of the lambda calculus which exist today, including the simple, untyped lambda calculus, the simple typed lambda calculus, system F, the polymorphic lambda calculus, system F omega, a variant of system F with type operators, and others. For this course, we will only cover the simple untyped lambda calculus. For those who are interested in finding out more, I would recommend researching about the Hindley-Milner type system and system F after completing this module. These are quite complicated and you don't need to know about them, but I'm just mentioning them for those who want to know more. It is often useful to think of the lambda calculus as a sort of assembly language for functional languages. This is because higher level functional programming languages like Haskell, OCaml and others usually translate their source code into an intermediate form of one of the many variants of the lambda calculus. Since it underpins so much when it comes to functional languages, I think it's important that you have a rudimentary understanding of the simple lambda calculus. This will keep you grounded and allow you to understand and appreciate what is happening under the hood when you are actually writing code using a functional language. We define functions within the lambda calculus by using what is known as a lambda abstraction. Before we consider lambda abstractions, let's think of a simple function in the traditional mathematical sense. Let's say we have a function called f, which has a single argument x, and the function body simply adds 1 to x. It is important to note here that the function has a name, which we've called f, just for convention's sake. We say that the function f is applied to the argument x, or more commonly f of x for short. So we can say f of 1 equals 2, and f of 2 equals 3, and so on. Now let's consider the lambda abstraction equivalent. Don't worry that this seems like an alien language right now. I'll explain what it means. Firstly, it starts with the lambda symbol, then an x, then a dot, and then the function body. The lambda symbol denotes that a lambda abstraction is being defined. The x is the formal parameter to the lambda abstraction. A note on the function body. In the lambda calculus, function application is always written in the prefix form, so the plus is always before its arguments. It might be a bit weird to see at first because we are taught to place the plus in an infix position in mathematics classes, but you will get used to it after a while. After all it symbolizes is that you need to add x and 1. The position of the plus can be prefixed, infixed or postfixed depending on the convention you are using. All lambda abstractions have this form: the lambda character, the formal parameter, which we call variable for short, a dot, and then the expression representing the function. Unlike the traditional mathematical function f, the lambda abstraction does not have a name. It is said to be an anonymous function. This is an important point. In the lambda calculus, functions do not have names, they remain anonymous. Sometimes it might be convenient to give a function a name, especially if the function is essentially being repeated, but strictly speaking, it is not necessary. Variables to a function are given a name. In this case, we have given the single variable the name x. So how do we actually apply an argument to the function then? What would be the equivalent of the traditional f of 1 and f of 2? You will see in a later section on beta reduction how we define this formally, but for now, just know that you place the argument you want applied to the function after the lambda abstraction, like is shown here. So placing the constant 1 after the lambda abstraction is kind of like f of 1 in the traditional function. It will result in 1 plus 1, which equals 2. We add the additional brackets to remove any ambiguity. This style of applying the argument to the function is known as juxtaposition. Juxtaposition just means putting things next to each other, and juxtaposing the constant 2 after the lambda abstraction is kind of like f of 2, which would result in 2 plus 1, which is 3, and so on. You could, if you wanted to, juxtapose another lambda abstraction after the original lambda abstraction, but we're keeping it simple here for now. So, to summarize, A lambda abstraction is essentially a way of defining a function in the lambda calculus. But what exactly is the lambda calculus? Take a look at the figure which I've taken from the book by Simon Peyton Jones. The book is available for free at the link in the footer. This is a version of the simple untyped lambda calculus, which we will use throughout this module. This definition is written in BNF, which stands for Backus-Naur form. This is a simple way of describing the syntax of a language. The symbol : equals can be read as is defined as, and the pipe symbol can be read as or. Anything within the less than and greater than sign is a name for a class of symbol within the language. So a constant, or variable, or function application, or lambda abstraction. This may seem slightly complicated right now, but don't worry, you will understand it once I've finished explaining. And so, we can see that the lambda calculus is a language which allows you to define an expression, where an expression is defined as a constant, or a variable, or an expression placed next to another expression, or a lambda abstraction. We've already seen lambda abstractions, so this part should make sense already. The first thing to note about this definition is that it is recursive. That means that the thing we are defining, expression, is defined in terms of itself. For our purposes, we assume that the constants defined include all numbers as well as all inbuilt functions like plus, minus, multiply, divide, and the booleans true and false. Where appropriate, we also allow the usage of brackets to group things. This is to avoid ambiguity. Let's now look at a lambda calculus program. The program is very simple on purpose. Calculate 3 multiplied by 4, which is obviously 12. But the point here is to illustrate how the syntax matches the definition in the figure. So this program is an expression, which only uses two of the definitions to the right of the : equals sign. That is the constant and the expression placed next to the expression. Let's see how this very simple program maps to the syntax in the figure. We go through a transformation sequence which takes 10 steps in total. Firstly, we start with the single expression, which defines a lambda calculus program. Since a single expression can be defined as two expressions placed next to each other, we can replace it with that. Now a single expression can be defined as a constant, so we replace it with that. We can now replace the symbol representing a constant to the actual constant in question, which for us is the multiplication function, which we have assumed to be a built-in constant in our definition of the lambda calculus. Now we can again replace the single expression to two expressions placed next to each other. Like before, we can replace one of the expressions to a constant, and like before, we can replace the constant symbol with the actual constant we want, which is 3. We can then do the same with the last remaining expression, except this time we want it to take the constant value of 4. Additionally, we add the final brackets to the program. You can see now that since the single expression is defined in terms of itself, we can build up a much longer expression, which, although in this case was quite simple, could grow to be quite complicated in a real program. So in summary, the lambda calculus is a simple language in which you write programs in. Your entire program is a single expression, and the program is executed by evaluating the expression. In this case, the expression is multiply 3 and 4, which would obviously evaluate to 12 when the program is executed. Here is an exercise you can do to confirm that you have understood everything so far. It is slightly more complicated than the previous example in that we are using the lambda abstraction. You need to create a sequence, like I did for the previous slide, to show that the following is a valid lambda calculus expression. So start with the expression and build the rest of the sequence. Pause the video here and try it for yourself. It is not that hard, but can take some time just to work through each of the steps with a pen and paper. Okay, let's work through the steps. We obviously start with the expression. Then we can replace it with the lambda abstraction. Then we can replace the variable token with a variable name, which we want to be x. We can then replace the single expression with two placed next to each other, i.e. an application. And then we can replace the first expression as a constant, which in this case will be the plus function. We can then replace the single expression with an application, i.e. two expressions next to each other. Now we can replace the first expression with a variable, which we call x, and to get to the final point, we replace the last expression with the constant 1. Hopefully, that wasn't too difficult, and now you understand how we can build larger and larger expressions in the Lambda Calculus. This video is a clip from a longer video where we explore the Lambda Calculus even further. Check that out if you want to see more.